linearization is not exactly something that you need formally for the IB diploma, especially for physics. However, it's implied. You need this a lot. So you won't really find this in a book, I don't think, like exactly called linearization, but this skill is really important. So that's why I thought it warranted its own video here. So this idea of linearization really hinges upon this word linear. And linear means line. So what I'm going to do is really focus on lines here. So do you remember the equation for a straight line? Remember this from math. It goes y equals mx plus, now some people use b, some people use c. It doesn't matter. So this is the equation of a straight line. So if I actually want to graph that, let's see if I can do it nicely here or not. I'll just try here like this. So if I want to do a graph of it, let's just see here. So like this and like this. I think I have to do it again here. Let's just say, so something like this right here. If I actually wanted to do a graph of this, right, x and y, then do you remember how these go? What features are there? I mean, the y and the x have to remain y's and x's. The m is just a number in front of the x. And whatever that number is, and keep in mind, I know you're probably wondering, like, what? I know this. Watch carefully. I'm going to remind you of this, and I'm going to do some sneaky things that are actually going to end up being linear graphs, okay? So bear with me in case you think this is too easy. I agree, this is supposed to be really easy, this part right here. So remember this junk, whatever is in front of the x, no matter what it is, it can be a bunch of stuff, complicated equation, but whatever junk is in front of the x, that is your gradient. Some people call it your slope. Same, right? So gradient. And then remember what b is? B, or whatever this is, you're adding or subtracting to your x's, that is your y-intercept. So in this case right here, then the general sort of graph then would look like, I don't know, maybe something like that. So this could be something where, the y-intercept right here, this right here would be b. So whatever that value is here, that'd be b. And this slope, remember how we found the slope? The slope would be, slope or gradient, right? Gradient and slope are the same thing. So slope, which is equal to the gradient. In this case here, that'll just equal m. And do you remember how to find it? When you do delta y over delta x, or sort of people call it rise over run. There's a lot of ways of seeing it. Now that, of course, seems probably too easy, and I love this little meme here. So here is your line graph. A lot of people use this one image here, and they don't really attribute it to the proper source, but I guess I didn't hear either, but I'll tell you about it. It's actually from a blog called Hyperbole and a Half. It's a blog that's brilliant, absolutely brilliant. So let's do an example here with springs, with Hooke's law. If you know about springs and Hooke's law, maybe you don't. I hope you know about it. So this one here, imagine I have a spring here, and I attach to that spring some sort of mass here. And of course, as I add more and more mass, the spring extension itself, it'll extend even more. So I could see that the extension is related to the mass that's been added. So you might then end up doing a whole bunch of different values, right? You could actually, have different values in a table of the force, the applied force, which is related to the mass, right? Mass times acceleration due to gravity. So force would be in newtons. And you would also have related to that the extension. So x, that could be like the displacement. And Hooke's law goes like this, that F equals kx. It's technically got a negative. It tells you about the force is in opposite direction to the extension. I'm going to ignore the negative for right now. I'm just going to say F is kx. Now keep in mind then of what this means. So you have a whole bunch of values here of F versus x. And you have uncertainties on them, sure. The key thing though to remember here is that what would you need to graph against what to get k? See, very often on exams, especially on paper 3 now, they're going to be asking you to somehow determine some sort of value. And it won't necessarily be k, so don't memorize this. But I want you to learn how to deal with this and how to look at this in the right way. It may not seem so obvious, but can you see that this one right here, I can see this as a linear graph? Can you see that this one right here, this could be my y. My x, hey, that's actually kind of nice. X could literally be x. That means whatever junk is in front of the x, remember, that's going to be the slope. And that means that whatever I'm adding here, in this case here it's 0, that would be the y-intercept. So what this tells you then is really cleverly, you can already know what the graph is going to look like. You could actually sit there and know that, okay, well, if I graphed, in this case right here, let's see here, the force in newtons versus the extension or the displacement in meters, then what would the graph look like? You know what it's going to look like already. Look, it's going to be a straight line graph that passes through the origin, so it's going to pass through here, and it's going to have a slope of something. I don't know what, whatever. Whatever that slope is, let's just see. Oops, I can't seem to draw a nice straight line. Maybe I'll do it this way instead. Draw a line. Let's see if it works here like this. I suppose technically it could go in the negatives, but you can't have negative extension. Well, I guess you can. You just go up above. But let's just leave the positive for now. So this right here would be the graph. And if you're really clever about it, then you could use that graph to tell you, oh, I know, I'll find the slope of that graph because that slope will literally equal k. And what will its units be? The slope's units will be, well, remember, slope is rise over run. It's y over x. So in this case here, it'll be newtons per meter. Okay, so it'll be in newtons per meter. So this right here is how we can linearize this. I'm going to give you another example. So with the pendulum, I love this one here. So how often does one make jokes about IB physics with pendulums? Periodically, haha. That's actually because I had a video a while back that I did actually about a cat, and you could actually hold the cat up and actually make the cat be a pendulum. So it's called pendulum cat. You can look it up on YouTube. But what I want to show you is that there is a pendulum equation. There's actually one you get. It's in your data booklet, and it goes like this. Maybe I'll put it in green. There's a pendulum equation. It goes t equals 2 pi times square root of L over g. And this is the equation for a pendulum. Okay, so you don't have to memorize it. You can look it up. But this particular equation is really important because what it tells you is that if you were measuring a bunch of values, so let's say you're taking data and you knew the period and you were manipulating the length. So those are the two things you'd be changing, the period and the length. The period is in seconds and the length would be in meters. And you have different values of period and length, right? So you manipulate the length, you change the length of the pendulum. In this case of pendulum cat, you're having different cats of different lengths, I guess, technically. You let them, operate as a pendulum, and you measure the time it takes to do one full motion. That's one period here, in seconds. Now, if you were to graph t versus L right now, okay, so I'll just be a little bit lazy. I won't use nice straight lines. I'll just graph L in meters, and I'll graph t here on the top here. What would the graph look like? If you look at this, t versus L, well, the 2 pi, and by the way, g is just acceleration due to gravity, so you can kind of ignore that for now. The way the graph is going to look, it's going to look like y equals square root of x, won't it? Because it's got t equals just square root of your x value. Remember what square root of x value looks like, or graph looks like? It does this. So here's the problem. Using this graph, how am I going to linearize it? How am I going to take the slope of this graph to find g? I can't really. I mean, you could do individual values of t and L, but that's not the best way at all. The best way is to use a linear graph. So this is not helpful. So rather, a better thing to do is to actually manipulate this equation. I don't like the square root. So what am I going to do? I'm actually going to square both sides. So I'm going to square both sides. I'm going to see t squared equals, let's see, 2 squared is 4, pi squared is just pi squared, and square root of L over g, that's just L. And I'm going to do over g over here instead of over here, just so it looks a little bit prettier. Because look carefully. It doesn't look like it, but this is actually linearized. Look at this. This junk right here can be y. This right here can be my x. If that's the case, whatever crap here is in front of it, that's the slope or the gradient. So that means if I was to do a graph now, let's just actually draw it here. So if I was to do a graph at this time of L in meters versus t squared, so that would be in seconds squared. If I was to graph this, I know it's going to be a linear graph and the y-intercept is 0. So that means it's going to pass through the 0, 0. It's going to be some graph that's going to go like this. And I know furthermore that the slope of this graph is going to equal 4 pi squared over g, which means I can actually literally then find the slope of that graph. And if I did that, can you see I can manipulate this? I can use that graph then to find g, because I can just rearrange this, right? Cross multiply, as people call it. G goes over here and the slope goes down there, so it's going to be 4 pi squared over the slope. That will be your answer. That is how you will actually use a graph of t squared versus L. And just that graph then, you know it's going to give you a straight line because you're smart, you know about linearization. And you know then that the g is actually going to be found literally by the slope. In this case, the slope is going to be 4 pi squared over the slope. That's going to be what g is. So you can actually find the acceleration due to gravity. Isn't that cool?